Hello all, so let's continue with our probability series. Now, we all know from our school days that what is the definition of probability? It's like number of favorable outcomes. Let's say we have an event E, then what is the probability that that event E will occur? So, number of outcomes favorable to that event E in the sample space divided by total number of outcomes that we have. So, in short, we take this definition as it is, right? But there should be some mathematical proof. Though it is intuitive, it's like a proportion, right? That if tail occurs twice out of four times, then we can say that 2 by 4, right? Just the frequency based thing. But what can be the proof for that? But before that, let's solve one quick example on probability, because this is the very first example that we are solving in this series, and this will be based on one of the previous formulas that we have seen. So let me read it out. So it says that a total of 28% of American males smoke cigarettes, 7% smoke cigar, and 5% smokes both cigars and cigarettes. So we are asked to find what percentage of males smokes neither cigars nor cigarettes. So we need the males that smokes, like they are non-smokers. We need that. So let us define our events. Let E be the event that any random person, okay, so random has a deep meaning here. So any random person chosen at random, any person chosen at random is smoking cigarettes. And similarly, let F be the event that any random person is smoking cigars. So what firstly we will find, like, what is the probability that we have a person smoking either cigarette or cigar. So that can be union of this, because union, what this will give, let me write by changing a color, this will give a person smoking either cigarettes, I'm not writing the entire spelling, but it is cigarettes or cigar. So we know this formula, that P of E plus P of F minus P of E intersection F. Now we have 28% smoking cigarettes, and we have defined E as person smoking cigarettes, so we will write this is 0.28 in terms of probability. Similarly, this is for cigar, it's 0.07, and for both we have 5%, so it will be 0.05. So on and all, this will be 0.3. So what we can say, that the probability that whether a person will smoke either, so he's a smoker in short, either he smokes cigarettes or cigar, doesn't matter, but he's a smoker, right? So what is the probability that a person is a smoker? 30%. So we can say that 30% of American males are smokers. So what we are asked, we are asked that what percentage of males smoke neither cigarettes or nor cigars, right? So what can be that? It will be simply the remaining, which is nothing but 70%. So our required answer is, in percentage, is that 70% males in US smokes nothing. They are non-smokers, right? So that's it for this example. Now let's continue with the proof of this, and we'll be utilizing the axioms that we have seen in one of our previous videos. I think the very last video, I guess. Yeah. So let's continue. Firstly, we know that in a sample space, let's say we have some sample space denoted by S, and let's say it has n number of outcomes in total. Now we will not be biased here. So here we will say that each outcome, right, in the sample space is equally likely to occur. Equally likely. Now what does this mean? For those who don't know, for example, let's say we have a coin and we have two possible outcomes, tail and head, when we toss it once. So it should not be biased that like maybe we can somehow modify the coin in terms of weight or something, and always tail occurs more when we flip that coin, then it will be biased, right? But we don't want that. So in this, what should we have? That's why we say a fair coin is tossed, because we don't need any bias, or because this will be a cheating, right? If there will be bias, then so we will say that both has probability of occurrence of zero point 0.5. It's not like we are on the either side. We are not biased to any side, either tail or head. Similarly, for more number of outcomes, let's say n here in our case, we will say that each is equally likely. And let's say the probability is p for each of them, because we need, so it's bad to write this is equals to p. It seems like sample space equals to p, but let me write the other way around. That is, the probability of occurrence of 1 is equal to probability of occurrence of 2, and similarly we go for the very last one, that is n. Correct? So this and this is equals to p. Let's say p is some probability. We are just assuming. Now we will use our axioms that we utilized before. So we know that from our axiom 2, maybe they are here only. From our axiom 2, we know that probability of sample space is 1. We discussed in detail in this video. So I'll request, if you can't recall, just go through that video again. So we know that P of S is 1. And we know what is S. We are just writing S as all this 1, 2 up till n, because our sample space consists of n points. And since they are independent, because if one occur, two cannot occur, right? At the same time, I mean. So they are mutually exclusive. So we can write like this: P of 1 plus P of 2. Let me write with proper notation: P of 2, and so on until P of n. We can write like this, right? And we know that for occurrence of each, the probability is p, and we have n such probabilities. So we will write this as np at the end. So in short, our last and final expression is np equals to 1. Why 1? Because we have p of s as 1. So this implies that what is the probability? Probability is 1 upon n. So if we have n possible outcomes in our sample space, then the probability of occurrence of each will be 1 by n. And let me just relate it with the coin toss example. Let's say in coin toss example, n will be just 2 in our sample space, head and tail, if we toss it just once. So n is 2. So what will be the small p value? This is small p. So what will be the small p value? That is the probability. It will be 1 by 2. And as I said, it will be, we are not biased to any head or tail, right? So the same thing applies for n number of outcomes. If we have, let's say, capital N number of outcomes for a general case. But now how we prove the, let me just remove this. It looks little better now. So how we can prove this statement that I wrote in the very top? This statement, how can we prove from this p equals to 1 by n? This can be proved easily, because now what is the p? P was, what was the assumption of p? P was the probability of occurrence of one event, right? One outcome, not one event, sorry, one possible outcome of total of n outcomes that we have, right? Now let's say we have some event E. Then what can be the probability of that? Because this is just occurring once and we are dividing by n. So for event E, what we can write? We can simply write how many number of points or like favorable outcomes that we have in set E, divide by total n. So I hope this is intuitive, that this small p over here was just 1 by n, right? And what was the definition of small p? Small p was probability of, what is the probability that 1 will occur? So we have all equally likely probabilities as p. So these are one individual points in our sample space. But let's say we have some event E which has some portion of this point, because in sample space is having all possible outcomes. So some event E will be having some subset of these points that we have in our sample space. So what are the number of possible points or outcomes in E? To be precise, if we are tossing a coin twice, then we have four possible outcomes: tail, 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 head, tail, and head, head. So let's say this is the sample space, all possible outcomes. Let's say we are saying that what is the probability that head occurs both the times? So it will be just once. So we can write we have just one point that is favorable to our event E divided by 4. But if we write what is the probability that at least tail occur once, so all this will be favorable because here also tail occur once at least. So then it will be 3 by 4. So I hope things are clear. This is just a mathematical way or the intuitive way to see the frequency definition from this generalized way. And this is really important because we should have equally likely outcomes, which is almost the case in every real life scenarios. And even in machine learning, we will assume the same. So I hope you got clear about this definition. So stay tuned and we will continue this series forward.